right, so good morning. I am also thinking the same way. Where is everybody? um, Perhaps there are already a lot of people abusing my convenience that I'm offering by hosting the lectures live and posting them online. So probably next time we'll do something in class as a way to have some participation. One of the things that probably you might not think about or realize is that when you're here in class, you're actually also, to whatever extent you're asking questions or somebody's asking questions, you're benefiting each other and engaging in the class. So thank you all for being here. We're pretty much done with the stuff that should primarily be review now, and going to be diving into the course content. And I think the roster is probably set now, so I will be a bit more formal with class participation, things like that, moving forward. Okay, so spread that news around. We did have a few people kicked out of this class to go to the other section, so it's probably going to be a little bit smaller than it was our first day, but there still should be like 20 people, something like that. Okay, I did post your first homework assignment, so that's on Moodle. We'll have that one due, I think it was the 15th, 14th or 15th, it's 14th. And then that'll give us time for one more. So that first homework is going to cover the intro material plus the sedimentation that we'll get into today, and coagulation. And then the second homework will cover a couple different filtration styles, the granular media and membrane filtration. And that'll lead us to the first exam, which we're still going to aim to make it on schedule for that. Okay, last time I left you with a bit of confusion on my part. I apologize for that. But for the scenarios where we're dealing with non-steady state conditions, and we have a little bit of more calculus to do in terms of rearranging a system. If you recall, let me go over here. We had talked a bit about the step function situation and that we could find a C at infinity, and that may be helpful. And then I didn't really connect how that's helpful very well for you. So if we take a mass balance, and we made a mess of this page last time, so I cleaned it up and highlighted something here. If we take that mass balance, first of all, we can solve it for C at infinity. Even if something changed, we can solve the new C that we will find by setting this part to 0 to say, well, eventually we'll reach steady state. So eventually we'll find a new steady state, and that's our C at infinity. And so the way to use that is then to find a way to take our generic mass balance that's not yet at steady state and find it in terms of that steady state condition, the C at infinity. And so I was getting a little bit confused at how they managed to incorporate that. Spent some time looking at the algebra, and so essentially what they did was they just forced it to have that term. And the way they did that is they said, well, when we solved C at infinity, we saw this became a denominator here, Q plus KdV. And so when they took a look at the overall mass balance, they're just going to extract that out of the entire thing. So like factoring it out, which was kind of convenient because we do see the same, that same Q plus VKD here. So when they just divide everything by that, you pull it out here, so factoring it out. But in order to factor it out of this portion on the left here, you just end up dividing by the Q plus VKD. And that goes right here. And so then you're left with this term, you factored it out, and you're left with this term right here. And that portion is our C at infinity. So ultimately, all that said, they found a way to put it in terms of C at infinity. And so they rearranged a little bit and said, okay, well, we've got this factored out. They pulled a negative out as well, so it's this Q plus VKD times the C minus what becomes C at infinity, and we'll say all that is such. And then we're going to just call that Y, because why not? So that gives them a way to integrate it, and from here we see we can integrate it just like we would pretty much anything else, and then when we substitute it back into place, then we need that C minus C at infinity. Okay, so I just wanted to clarify that. I definitely did not make that clear last time. So this is in the notes that we went through yesterday. I added it in before I posted it. So this is there for you to take a look at. And in addition to that, when we went to try to apply it to our system here, essentially the same thing applies. We find something for C at infinity and find a way to get our mass balance in terms of that C infinity so we can simplify our equation. So in this case, we started out with V dc dt equals QC naught minus QC minus VK for a zero order decay in a CSDR case. We could solve C at infinity. We did that and said, okay, C at infinity is going to be equal to C naught minus theta K. And so when we go to solve this, we can look for a way to get C naught minus C minus theta K somewhere in our mass balance. And so I had started it off like this and divided everything by V, and here is what we had. And I think if we take a slightly different approach, and start with our mass balance here, we can divide everything by V, that's fine. But what we'll notice is we can then extract out a 1 over theta because Q over V is 1 over theta. So 1 over theta, theta is V over Q, so 1 over theta is Q over V. And so we get a 1 over theta in two of the terms, and that'll leave us with a theta in that last one. Because if we divide by 1 over theta, that gives us theta. So that gives us, when we extract the 1 over theta out, that gives us C naught minus C minus theta K, which is very close to what we're after in terms of the C at infinity. So we can get that in terms of 1 over theta C at infinity minus C, extract out the negative, and that's negative 1 over theta times C minus C at infinity. Then we can treat that as our Y and solve from there. So then if we say that, then we're going to do dy over y, because we'll divide that to the other side, equals negative 1 over theta dt, and we integrate like that. And when we put in the terms later, we just have to account for what's y naught versus what's the current y. Okay, so that's, just wanted to clarify that a bit, touch on that because I left it off on a kind of confusing note. Does that make some sense? All right, so it's kind of typical for these things to, if you do get confused, it's typically what are they doing with the algebra here? And like I said, what I want for you to learn is that there is a process here that we can do. I'm not as interested in testing your algebra skills and creativity on exams so much as I am interested in seeing your knowledge and ability of taking a mass balance approach, recognizing what that algebra is probably going to look like to get there in order to solve a problem, right? So I'm not here to grill you on the in-depth calculus and algebra required to get there. There's going to be some of it, but I'm not going to give you the most advanced stuff on exams. Okay, so let me pull up the other slides. So we left off about here last time, talking about what does a typical surface water treatment plant look like. If we were to take a groundwater treatment system, it could be as simple as bringing it out of the ground, testing it for certain parameters. Groundwater is usually pretty stable, consistent across time if we have a good source, and disinfecting it and sending it along. That's approximately what we do in Baton Rouge. Of course, some scenarios you might have some iron you want to remove or something like that. So it can be more complicated, but our conventional design, I guess, if there is to be a convention, or the one that really captures the most commonly used treatment steps, would be a surface water treatment plant. So what we would do, taking water from the Mississippi, for example, would look something like this guy. Maybe, given the Mississippi is by the time it gets here is a little bit dirtier, we might do a little more than disinfection. Maybe we'll do some advanced filtration or some advanced oxidation processes to clean up, whatever chemicals might be in there that we don't want to drink. At any rate, we're going to take a look at sedimentation today and hopefully get to the point where we're also talking about how coagulation can then help before a next set of sedimentation. So what we're going to talk about today applies, of course, to both sedimentation chambers and also to what we would call a clarifier in the wastewater context. So this stuff, it's actually not as much mass balance. There's a bit of it. It's actually a little bit more of physics. So we're going to just take a look at particle settling velocities and how to use that and a force balance to get our design criteria for understanding basically how big of a tank do we need in order to sediment the particles we have to remove. Okay, so we want to use gravity, right? That's it's cheap, it's effective, pretty reliable. Maybe if we needed to treat water on the moon, that might be a little different. Might be looking for a different technology other than sedimentation. However, we can consider some particle. It probably is going to be some random looking thing, and if we make some assumptions, the math becomes pretty straightforward. So we can assume it's a perfect sphere. It's not too bad of an assumption with small particles. Some of them aren't going to be a sphere, but they're going to be close enough to act like one in a lot of ways. So we're going to make some assumptions here and say we're going to assume it's a perfect sphere. And then we have a few things we can look at. First of all, we have the force of gravity, Fg. Then we're going to have two upwards forces. Well, one for sure upward is a force of buoyancy, Fb. And then if our particles are sinking, then we have an upward drag force. Now, occasionally we might have a scenario where we actually cause particles to float. There are reverse sedimentation or flotation systems. You can add in really small bubbles to a system. They'll stick and attach to particles and cause the particles to float. That's actually effective in some scenarios. In that case, we would have a backwards, the force of drag is always going to be opposing where it's going, right? So we're going to assume with sedimentation, given the name, we are using gravity and actually sedimenting rather than using the buoyancy and floating. But the same principles would apply otherwise. So we'll have a force of drag in the upwards direction. That will be proportional to the downward velocity. So we've got the gravity, the buoyancy, and the drag forces. And so the challenge here is that we need to find a terminal velocity, like a skydiver, right? You want to know at what point do these forces balance in terms of, if you're going very slowly, there's not much drag force. But as you go faster, that drag force increases with speed. So you will find some steady state in terms of velocity. And we want to find that velocity because if we have a straightforward velocity to use in our calculations, it really simplifies the system. We can just say, okay, they're all going to move at this constant velocity. Much easier to deal with than some acceleration. Okay, so then this will ultimately be our design tool of some sort, or feature, is that velocity. So we can take some mathematical representations. So the force of gravity is going to be the mass of the particle times the acceleration due to gravity, so mg. The buoyant force is going to be the mass of the water that's displaced by that particle times the force of the acceleration due to gravity. And then the force of drag is going to be 3 times the dynamic viscosity of water times pi times the settling velocity times the diameter of the particle. So this terminal velocity we will call settling velocity, Vs. So a given particle that's in our system, we expect to find this terminal velocity, and here's where we see it in our force equations. That's where we can solve for that Vs and find that terminal velocity in that manner. So when we write up each of these equations, one thing you'll notice, so I mentioned that it's like the mass times the acceleration due to gravity, all that. There's another way we can write it, because it's hard to measure the mass of a tiny particle. If you've ever tried, you'll know even our best scales in the laboratory, they go down to maybe 1/10 of a milligram. Really, really, really good ones, maybe a little bit further. But we're really talking about, tens and tens of micrograms is what we can maybe measure. And now we're talking about particles that are maybe on the scale of like 1 micrometer, and are probably going to weigh a lot less than that milligram scale that we can weigh confidently. So instead of weighing them, we can get a bulk density by collecting a bunch of the particles, measuring the volume that they're occupying, maybe get some size measurements. There's some convenient ways to measure particle sizes just with a light scattering system. I can tell you more about that if you're interested. So we have some good ways to measure the size of them. I mean, even filtration could give us size. Okay, is the particle coming through this membrane? Then it must be smaller than some particular size. And we have ways to get the density. So with the size, we can get a volume, again, assuming it's spherical, and we can get a density. So rather than use mass, we're going to use volume times density. So this is essentially mass is going to be equal to the volume times the mass per volume, right? So that's what we're putting in for these sections, and then this will be the density of the particle compared to the density of the water. And the density of the water is going to be a known quantity. It's just going to depend a little bit on the temperature of the water. Okay? So this is getting us to a point where we can solve our system based on what we know about the particles and based on what temperature we're operating at. So we're going to put these together and solve here for this force balance. I'm going to go ahead and put all the definitions up here for each of these parameters and their units so we can see them clearly. Mu, this was the dynamic viscosity of water. Vs, the settling velocity. We're going to keep this in meters and seconds. So, these particles will be settling, and it's going to be a small number of meters per second. Right? It's going to be a fraction. We're not going to do 1 meter per second particle settling velocity. That would be extremely fast for a particle to travel through the water like that. We're going to have dp is the diameter of the particle, acceleration due to gravity, the mass of the particles, the volume, and the densities of the particle or water. Okay, so when we do a force balance then, and I think I've got another slide for that. So we're going to say that our force of gravity, so our downward force, is going to be equal to the 2 upward forces. So, this Fg is going to be equal to the force the buoyant force plus the force, the drag force. So once we reach that, then we will have a terminal velocity. That's what we're going to solve for. So we can set this up to say, we're going to go ahead and use that V times the density of the water. So V particle, I guess we could say, so volume of the particle times the density of the particle times acceleration due to gravity is going to be equal to, again, the volume of the particle times the density of water times g plus 3 mu pi vs dp. Okay, so that gives us quite a few things there, and we want to solve for vs. So we're going to say, we'll just move this to the other side and say 3 mu pi dp times vs is equal to vp rho of the water times acceleration due to gravity minus vp rho particle times acceleration due to gravity. Then we can divide everything by this 3 mu pi and say that I'm going to keep the vs there for a moment, or the dp, I mean, dp times vs is equal to volume of the particle, and I'm going to go ahead and actually extract out the volume of the particle times the gravity here, and so we're left with the rho of the water minus the rho of the particle, the density that is, divided by 3 mu pi that we divided. Okay, so we're getting pretty close. We've got this velocity, we've got a diameter. Need to divide everything by the diameter. And before we do that, I'm just going to make a little reminder to say that the volume of a sphere we can define as in terms of the diameter of that sphere. And I might need a double check here. So I think it's 1/6 pi r cubed. Is that right? Or it's 4/3 pi r cubed?
I think it's 4/3 pi r cubed.
4/3 pi r cubed, and so when we put it into diameter, that makes it, we're going to cube the 4/3. What is it when we do the diameter? So 4/3 pi r cubed, which would be well 4/3 times 1/2 cubed, right? That's what I'm saying. That's what I mean. So that should be right. So 1/6. So that would be so 1/6. So that'd be 4/18. No, is it 3/4? All right, somebody looks up. I actually know the final answer, but what?
1/6 pi d cubed.
1/6 pi d cubed. Okay. Thank you. So we're going to put a little question mark there for a second. Okay. And so is it 4/3 here? What is the pi r cubed? 4/3? Yeah, that sounds right, and I'm just like blanking on the, okay. All right, so with that, we can substitute the pi dp cubed on top here, and so ultimately the vs is going to be acceleration due to gravity times rho minus rho particle times this dp squared, because we're going to divide by the dp over here, all that divided by 18 mu. The pi's cancel. Gosh. And that's what we're left with. So I just went ahead and left the dp squared on the other side of this. It really doesn't matter. This is just how the book treats it. And this is how it'll look on your formula sheet because of that. But basically we substituted in, instead of the VP, we used 1/6 pi dp cubed. So the pi is going to cancel. The 6 is going to go to the bottom and multiply with that 3 to give us 18. The mu stays there, and the dp on top, the dp cubed goes to dp squared because we divided by dp. So that's our settling velocity. So that'll be our tool to say if we have spherical particles, if they're staying the same size, if they're all the same size, and if they're not accelerating or decelerating or anything like weird like that. This is our design velocity. Okay, so we've got some assumptions built in there, but we can actually account for a lot of that or design accordingly to some extent. When we have a scenario where we're treating our water, we give it a nice, clean, slow flow, laminar flow, and it's just a system that's the way it operates. So you'll see these in practice quite a bit. Some of them will be circular, some of them will be rectangular. It actually doesn't matter too much one way or the other. We can use the same principle because what we have is a downward velocity, and then no matter where we're flowing it, what we're going to do is try to match the length of time where we give it to flow with how fast it takes or how slow it takes for it to reach the bottom. Once we reach the bottom of a sedimentation chamber, it tends to stick to the ground, maybe stick to other particles, whatever, and we call that settled. And we'll collect water off the top of the other end. So water will typically go, for example, if we have a circular chamber, it's going to go out radially to the edge. The particles are falling down along the way, and then the water is collected over that edge as clarified water, water that particles have been removed from. Likewise, we could do it in a kind of horizontal manner or a rectangular manner where water flows by and then is collected off the top over here, something like that. In the case of our, in either system, we can take a cross-section to say if we put our perspective like halfway into the swimming pool, like we got down, and let's imagine a swimming pool as our clarifier, and we take a look as water's moving to the side and the particles dropping. That's my cross-section here. What we want to know is a particle that started at the top, it needs to reach the bottom of our chamber before the water exits the chamber. Because if the particle doesn't reach the bottom, we assume that it kind of gets caught up with the flow and is taken away. So if it doesn't reach the bottom before we reach the side, it's not separated. And so what we'll do, and I should have not made so many dashes here. What we want to do is say, for our design, this line here, if I make it meet the bottom right there, that's the particle that will settle out. So the velocity component going downwards, Vs, is going to be important, and it's going to be related to the flow rate that's going across. Okay, so we're going to just take a look at a bit of math, how we can kind of take a design, and again, by the way, this rectangular looking approach, this cross-section, we will also get a rectangle if we took the cross-section inside a chamber like this, right? So we would see the particle travel, and is it going to reach the bottom before it escapes the circular chamber? So it actually doesn't matter if we've got a circular or a rectangular chamber, we can still get a rectangular cross-section to think about in terms of what's happening. Okay, so let's focus in on this. The particle that we really want to remove is the one that starts at the top. Okay, it's if we have any sedimentation at all, the particle that starts down here is very likely to hit the ground before we go anywhere, right? Now, if we have very, very slow sedimentation and we're definitely not reaching all the particles, maybe it's meaningful to look at, well, what portion of them will we remove? We'll get to that in a few minutes. But for the most part, what we want to do is design with this critical settling velocity in mind, where that particle is the particle, or the speed at which a particle is going, that is the velocity that's going to get complete removal of all particles in the system. Because all particles in the system are moving at least, are moving that fast, and anything that started below it will automatically be removed. So we're going to say that the settling velocity is going to be equal to what we would call a design or critical velocity at that point where this is that threshold. This is exactly the speed we need to achieve given the dimensions of our reactor. That's what I'm saying right here is V naught. And the difference here is that Vs is going to be an observed velocity, and V naught is going to be a critical one. That is the design of the reactor, of the chamber. It's kind of the definition of the velocity at which all particles will be removed, that or anything higher. So it's the minimum velocity that a particle has to be going given the chamber, given the setup. Okay, so we're going to define a few other things. We've got the height of a particle. Again, the one we're most interested in is the one that starts at the highest, but this would be HP. So for complete removal, we would define HP as the height of the total height of the reactor. Theta is the resonance time. Thank you for that question. So if we take a look at the time, let's see, the time at which it takes for the particle stays in the reactor, that would mean we have some amount of time from here to here. That would correspond to some distance, but it would also be some theta, right? So we have some amount of time in there. Okay. If we take a look at the height that a particle moves with a given settling velocity, and we could also, by the way, say that maybe this Vs here, Vs1 is equal to that, but maybe we measure some other Vs values. Maybe this is Vs2, and we could say this is Vs3. Imagine those are straight lines. So if we have three different settling velocities that we're considering, we see clearly that Vs2 is really fast, and we could design a smaller chamber if that's how fast they're going. Vs3 is going really slow, and if we need to remove all those, we either have to speed them up somehow, or we have to design a much bigger reactor to remove them all, right? And so if we have a given Vs, we can say, well, what height is it going to change over the course of our time here? The HP that it drops will be equal to the settling velocity times the time that we give it, right? So this is height equals meters per second times seconds, essentially, right? It's very straightforward. That's just saying the obvious distance is equal to the velocity times time. Okay. So I mentioned this already, but so the Vs is the particle settling velocity, V naught is critical settling velocity. That's the design associated with the perfect removal, the threshold of perfect removal. I'm gonna write that because maybe that makes sense. Okay, now what happens if we, let's say in the case a moment ago, we had our V naught. Now there's a question about what happens if we do have a system where our particles are not quite settling so fast. We can say that if this is our V naught, if our V naught is greater than our observed Vs, then everything's removed, because if it's greater than, if V naught is greater than, that means, excuse me, not all particles removed. Said that backwards. The Vs is slower. So if V naught is greater, that means the actual settling velocity is slower. That means they're not all making it out. Okay. If the reverse, and we have some case where, like we saw last time, if that's our Vs, then this one is greater than V naught, then everything's removed, no problem. Okay. Now there's something you might notice. If we had this guy here, this settling velocity, but we took a look at the particles that were halfway up the water column in the first place, there's a decent chance they're removed. And it's actually as simple as looking at the geometry and saying, well, how far up the midpoint, are we at the midpoint? Then 50% are removed. If we make a line between the midpoint here and the end, and that's getting perfect removal, then 50% are removed. So the way to write that would be to say, I think I have a slide on this, but we'll go ahead and talk about it here anyway. So if we were to say a particle started here and was removed, and that's like the threshold, if this is Vs, and this is V naught, we could take a look and say if Vs equals 1/2 V naught, then we actually have 50% removal. I'm fairly certain I have another slide on this to come back to it and write this up more clearly, but essentially we could say some portion, some percentage of these particles will be removed, and that should be equal to Vs divided by V naught times 100%. We're never going to have more than 100% of particles removed. So if Vs is greater than V naught, this fraction will be over 1, and that just means we have 100%. Right? So don't give unrealistic numbers. Oh, we removed 1,000% of the particles here. That's magic. Okay. I mentioned this earlier, but essentially it doesn't matter which type of clarifier we use. We can make an imaginary cylinder here, right? And say that in this imaginary cylinder, we can draw that cross section. What I do want to note here, and I think that's probably what I was actually intending this slide for, is that as we think about how the particles are moving through this system, we can relate the speed of the particle, or the flow rate, to the area of the system itself. So if we imagine, and I'm going to change colors again to kind of give a little contrast here. If we imagine that this is a rectangular system, looks something like this. The area of our basin is going to be this length times this width. And that's going to actually be very important for us to consider when we think about the flow rate as it relates to our residence time. So we know that theta is going to be V over Q, right? So volume over flow rate. Write that up like that. We also know we have some height of the chamber. And so we know that the theta is going to be equal to this height times the length times the width divided by some flow rate. Now, what we are perhaps interested in is taking a look at, again, how quickly the particles are falling compared to how long they have to stay in the system. And so when we consider this, we can essentially reduce this to be the area of the basin times the height divided by the flow rate. The height is going to be let's see, the height here will ultimately cancel out in some sense because the flow rate we have traveling across, if we were to put our Q and expand that out, we'll see in a couple minutes. I'll come back to this to just follow the notes appropriately instead of just talking off the off the cuff here. But we'll see that the height actually doesn't mean much. It's actually the area of the basin that means more. And the way to think about this is if you were to imagine spreading water out over a wide area, you know that that's going to be a smaller height, right? Just intuitively. You spread it out over long ways, the height is much more shallow compared to if you had a little channel and you flowed the same amount of water through it. And so when we think about sedimentation, the distance it has to fall might change, but if you were to take it and give it a small area, it's got a higher height, but you could give it a long channel. Or you could give it a short channel and a very wide channel, and it's going to have a small area to go, but a small distance to do it in. So it's going to work out kind of the same way either way. The point I think really just wanting to make here is for the area of a circle, pi r squared, or the area of a rectangle, length times width, we're going to use one or the other for that, and we'll come back to this in a second. So given that, we can actually accelerate our sedimentation with what we would call a high rate settler. And this is kind of a neat little tangent, but the way we do this is we can say, let's increase this area kind of artificially. And if you add shelves, you're essentially adding in a bunch of area to what would have otherwise been just the bottom here. It takes a little more maintenance. It's a little harder to collect all the particles and get rid of them appropriately, harvest them or whatever, and keep them out of the water. So there's a bit of maintenance challenge to it, but you can get a high rate settler by, this is 4 times or 3 times the area, a lot more area than they had at first just by adding in some shelves there. So there's some interesting little tricks you can do with that. Another small tangent here, we can design what we'd call an upflow reactor, where we have water flowing upwards, which seems a little counterintuitive because then your drag force is kind of moving with you in some sense. But what happens is, and this is used occasionally, what happens is you're harvesting water as it flows across kind of the top of some barrier. Your critical settling velocity is actually this velocity component here, because as soon as your particles are moving at least that fast, they're going to be traveling downward instead of upward. They're going to oppose the flow enough to make it to go the other way. So if you make a chamber that's kind of tapered outward like this, like it's shown, your velocity is actually going to be slower up here than it is down here. And so as you get close to the top, particles are no longer making it over. And in the real world, the particles then are more likely to collide, stick together, form larger particles, and then settle out better. So it kind of encourages the particles to collect a little bit here until they can sink further. So it's kind of interesting. It is an all or nothing design because if they're not below, if the velocity is not higher than the V naught, then you have 0% removal. So it's a bit of an all or nothing system, used occasionally for particular cases. Okay, so I mentioned I had a slide on this partial removal. If our V naught is greater than Vs, then we have this equation, percentage of particles removed is Vs over V naught times 100%. Okay, and of course, we cannot have greater than 100% removal. Okay, so in this case, we see the first line up here is drawn where it is not quite removed. So there's some portion here of particles that are not removed. And so that means that there's a corresponding portion here of particles that are removed. And given that we're dealing with a constant velocity, then these terms are actually making nice little triangles, and we could also correspond, the difference here is proportional either side. And so either way you look at it, it's just some portion here that we can define. And that portion would be equated by the ratio of the critical velocity to whatever sedimentation velocity we observed. Okay. All right, so let me take a moment, and I just am not feeling entirely awake today, so I want to make sure I speak this clearly and show you what we've got on our formula sheet for the sedimentation as it relates to our system. Okay, yeah, so all right, so in terms of the equations here, of course, I'm gonna go ahead and give you this equation on your formula sheet, the Vs term. And then in terms of while we're doing sedimentation, I'm gonna take a little bit of blank space here and just write this up a little more clearly. When we look at our flow rate and our Vs, or V naught, excuse me. V naught is what we want to relate to our theta. So we can say that the terminal settling velocity here, when it reaches there, this should be, we can arrange it so this is Q over AB. And I wanted to explain that. So like I said, we're looking at this system and we have some imaginary 3 dimensions here. We have a 3-dimensional area for our basin. If we think about the definition of a particle that reaches the bottom at that point, this is going to be some distance, we'll say meters over seconds, distance per time. And on the other side of this equation, our flow rate going through, and this is what I was trying to get to earlier, our flow rate through is going to be in cubic meters per second in this case. If we divide that by the area over which it's flowing, then we're left with just meters and seconds. Okay, so we're going to say the flow rate here, or the velocity is going to be equal to cubic meters per second divided by the square meters we're flowing over. So that's what I was trying to say, and I'm sorry I had a little bit of brain fog there. So when we design our system, the design velocity is related V naught equals Q over AB. Okay, this is that flow rate, and this is that example, right? If we send water, down the Mississippi, it's got a very deep channel, and then it hits the Gulf, and it spreads out, and we have a delta, right? And then it's the sedimentation system changes quite a bit. We've got a large flow rate, but it's over a massive area, and it slows down that velocity in some sense. So the Q over AB, this is holding true because this is the time we're defining V naught as the time it takes for a particle to hit the bottom, has that travel speed relating to the amount of time that it spent in the chamber. So this equation is going to be one of our design equations for sedimentation. It's just a relationship between how we designed our system and the conditions, the flow rate and the area. So essentially, the height of the chamber doesn't actually matter in terms of the design. It's just the area of the basin, how much does it flow over. Okay, I apologize for not being clear on that the first way run through. Does that make sense? Okay, so this one, it's simple enough that I should not have a brain fog, but I have not put it on your formula sheet. So definitely take a look at this one and remember that's the situation for sedimentation chambers. Really, because this is the distance a particle needs to travel given that timing. Okay, then this means we can also compare a given settling velocity Vs to this design and determine whether or not it will be settled. Or we could say to ourselves, we need to design a system and make a system that has a V naught equal to this particular settling velocity. So sometimes we'll take a particle and it settles, it has a specific Vs, and we say we need to make a system big enough to handle that. What are the dimensions of that system? Well, we come back to here to design those dimensions. Okay? So let's do a bit of practice. Let's take a look at silt removal in a clarifier. So we have a drinking water treatment plant that uses a circular sedimentation basin. So we've got a circular system. To treat 3 mgd of river water, so that's 1 million gallons per day, and it gives us a conversion there. After a storm occurs upstream, the river often carries 0.01 millimeter silt particles with an average density of 2.2 grams per cubic centimeter. The silt must be removed before the water can be used. The plant's clarifier is 3.5 meters deep and 21 meters in diameter. The water is 15 degrees Celsius. So the questions are A, what is the hydraulic detention time of the clarifier? And B, will the clarifier remove all the silt particles from the river water? So up front, we're given a clarifier with specific conditions, flow rate, all that. We're asked to find theta. And then we are asked to say, well, given these particular particles that are challenging this particular clarifier, is it going to remove all of them? Okay, so I'm going to give you a few minutes on this. and then we'll work together to find the solutions. Feel free to work together, ask me questions. I'm going to write up the equation in a moment for the sedimentation velocity. But go ahead and work on this a few minutes. Sorry, I think I wrote this backwards. It's supposed to be rho particle minus rho water. And the way to mentally check that is if the particle is heavier than water, it should sink. That should be a positive number. So normally our particle should be heavier than water. Okay, so hopefully you got a time to solve part A at least. Should be 9,221 seconds. So if we do the conversion for flow rate, it gives us 0.1314 cubic meters per second. And then the volume of this cylinder is going to be pi r squared times the height. So take the diameter, half the diameter, square that, and then times pi times height should give us 12,000 cubic meters. From there, we want to solve for both the Vs and the V naught that describes the reactor. Did I do something wrong? For the theta? It could be a rounding error on one or the other of our parts. I put it in Excel, and what I did was I just used 3.14 for pi. since I didn't have a, well, I guess I was lazy. So if we put out a few more digits, that gets us closer to, yeah, your answer. So I just used 3.14 and that was off a bit. Okay. Okay, so if we solve for V naught, according to this, it should be, what was it, 3.8, 3.80 times 10 to the minus 4 meters per second. This is taking our known flow rate and dividing that by the area of the basin here. Again, this is the critical velocity for this particular reactor, right? It's defined as what the reactor can do, essentially. So from here, we also want the Vs, and that's going to require, that's the G, the rho particle minus the rho water, sorry for that confusion, dP squared divided by 18 times the dynamic viscosity. So the acceleration due to gravity, I wrote up, it's 9.81 meters per second squared. The rho particle was 2.2 grams per centimeter squared. So we need to do some conversions there, centimeters cubed. And so we essentially want it in kilograms and cubic meters, okay? And you'll notice that our density of water is in kilograms and cubic meters. Before I do that conversion, I'll show you a little cheat code. The density of water, we can take a look at 15 Celsius, that's 999.1 kilograms per cubic meter. So the quick and dirty way to check your conversion here from the particle is that it should be approximately on the order of the other one. So without even knowing anything else, I'm going to say, I think this probably should be 2,200 kilograms per cubic meter. Now, we can go ahead and do the conversion properly and say we've got 1,000, let's see, 1 kilogram per 1,000 grams. And then we also need to account for the cubic centimeters. And so then we say we're going to have some number of cubic meters. Let's say every 1 cubic meter, we have some number of cubic centimeters. And so the conversion would be normally 100 centimeters in a meter, but we have to cube that. So we're going to have 100 cubed to get the centimeters cubed per 1 cubic meter. And when we do all that out, so 100 to the third power should have 6 zeros at the end, divide by the 3 zeros here, so we get 3 zeros on the back end of this, or 3 decimal places, so we get 2,200. Okay, so that should all work out fine. So the cheat code is that if we're actually settling particles, and it's not some sort of trick, then it should be approximately 1,000 or more. Should not probably be 10,000. That would be kind of crazy. All right, so anyway, we get that. We get the diameter of the particle. That's 0.01 millimeters, or that should be 1 times 10 to the minus 5th meters. And we can put all of that in. When we solve, we should get, put this also in scientific here, should be 5.75 times 10 to the minus 4. meters per second. So now we can compare and say, well, our V naught was 3.8 and our Vs is 5.7 of the same order. So Vs is greater than V naught. Therefore, all particles removed. Now the trick here, oh, I'm sorry, there's one other piece I forgot to label. The mu, again, we need to look up according to the table. That would be 1.139 times 10 to the minus third. I told you the first class, there's a trick here, right? And again, watch the units, right? So we have kilograms, meters, and seconds throughout. So if we had left anything in the centimeters, that would have been a problem. If we left something in grams, that would have been a problem. Once we have everything in kilograms, meters, and seconds, we're clear. And then this number comes out when we put all those into place. So the common mistakes here are actually just simply not managing the units properly. And then it's just a matter of recognizing how we relate the Vs to the V naught. Okay. Does that make sense? Checking the numbers still. All right. So once we have done sedimentation the first round, we're going to do coagulation dosing. I'm just going to give a quick intro to that with the remaining couple minutes just to try to make a little more progress. Certainly we're going to have more sedimentation, after the coagulation and flocculation process. We're not going to cover it again, so that's essentially the basics for sedimentation. We have the settling velocity, we can relate it to a reactor size, and we can basically take it from there. That handles all of our sedimentation. So what are we actually removing when we do sedimentation? Well, if we take a look at a typical scheme of different particle sizes, according to what we can conceive of, up here at 1,000 micrometers, that's 1 millimeter. That's the size of a raindrop, basically. 1 millimeter is something you can kind of see with your, with your eyes, or see it on a ruler, no problem. And if we define, mist, would probably be dropping below that. Maybe a very thick mist, you could see individual particles if you look really closely, but certainly there's some that you probably couldn't distinguish the fine particles, especially as you get to what you would call fog, I guess. Screen mesh, like in a screen porch, you can definitely see, but you'd have to maybe get really close to take a look. Human hair, you're pretty familiar with that, and it's pretty variable, right? If you look at an eyelash versus an arm hair or something, they might actually be different size in terms of the diameter, the thickness. Pollens, likewise, some of them you can probably see individual grains, but a lot of them not so much. We get down to algae and these cellular type stuff. We're getting down towards bacteria, things like that. Definitely getting past our visible eyes. There is a couple strange bacteria that are very large that you can actually see, but for the most part, anything we care about would definitely be smaller. And way down here at the bottom, below 0.1 micrometer, we're starting to get to the 100 nanometers, definitely past below our vision. In fact, they're below the vision of a microscope that's using photons, because wavelength of visible light is about 400 nanometers for violet, the most high intensity or smallest wavelength light. So we actually have to use different types of photons or different types of measurements to even observe what a virus looks like, because regular photons, visible light photons, can't do it. Okay, so this is kind of a scheme of particle size kind of stuff. This is relevant for not only sedimentation, but filtration. So when we start thinking about that last problem, we had 0.01 millimeter particles. That's putting at us at 10 micrometer particles. So what we're talking about as silt there is kind of in this range. That seemed to settle out pretty well, but as we'll notice, that velocity term had a square relationship to the diameter of the particle. So large particles will go fast. Once you start getting smaller particles, exponentially slower. So we actually don't really expect to be able to handle much at this range. So there's lots of bacteria that probably aren't taken care of. Definitely no viruses unless they happen to stick to a larger particle. So when we do sedimentation, it's helpful for a lot of stuff. You know, maybe we can get a lot of the pollen out or whatever. But there's certainly some limits here. And what we are aiming to do with coagulation is to gather a lot of this stuff and push it to the right to make it larger to stick together. So that's where we will pick up next time. How do we do that? How do we cause them to become sticky? All right, and a reminder, we'll probably do some sort of a in-class participation of some sort.